Right, for today's lesson, to start the journey into differential calculus, we need to understand the difference between instantaneous rate of change and an average rate of change. Average rate of change is when you have 2 points. That's what we call a normal gradient, and we've worked with average rate of change for a long time. You may have done it already in functions in grade 11, where you've actually calculated the average gradient between 2 points. Okay, now a gradient is basically a rate of change. Remember that a gradient basically tells you how the height of a particular object changes as you would have gone horizontal. So it's your change in the vertical over your change in the horizontal, which give you a rate of change. So in this case, you have 2 points A, B. Okay, and for you to calculate the average gradient between A and B, you will actually use the formula for gradient, which is YB minus YA divided by XB minus XA. So that is your standard formula for gradient. Okay, so if we can say that, or we can conclude that if a function is given in the form a comma or x comma f of x and x comma f of xb for the second point. Okay, now we are just assuming that this function is whatever. We're not sure whether that is a quadratic or a cubic function. So whatever the case is, we can conclude that this average rate of change can be calculated as f of x2 minus f of x1, or you could say f of xb minus f of xa over xb minus xa. And that is just your average rate of change. Okay, now what we have to do and what we want to do in this case, in calculus, we don't want to calculate the average rate of change. We actually want to calculate an instantaneous rate of change. And I'm going to try and give you this in a way of an example. In many cases, when we do speed time graphs or distance time graphs, so here we have the distance in meters, and here we have the time in seconds, and we say, so this is the journey of a particular object, and you've probably seen it this way. So something like that, it goes this way, and then do something like this. So this is a typical distance time graph. Okay, now what you've learned from a distance time graph is that you could calculate what was the average speed of the journey between, let's say, point A and point B. And because from point B to point C, your line is flat, which means that the time is passing, but the distance is not increasing. The distance from your origin is not increasing. That means that this object is stationary, is not moving. Okay? And again, from C to D, the object again is in motion, perhaps a little slower than it was here. And what tells me that? How steep my gradient is. Now, between D and E, again, we have a flat line, which means that my object might be at rest again. And then between E and F, which is the last point of my journey, remember, this is not the object is decelerating. Remember, the object is returning to the origin. Remember, this here represents how many meters from the origin I am. So that means the journey coming back. And again, when you look at that, you will have a gradient, okay, which will basically tell you what is the average velocity of this object at any given time. And that is how we've done it in the past. However, okay, the average doesn't really tell me the true story. Let's say, for example, I want you to take or think about, let's say you're going from Johannesburg to Durban. Okay, so this is now the distance, and we're talking kilometers. Okay, and this is the time, and now we're talking hours. Okay, and you're going to go from here to Durban. Now, are you going to tell me that your journey to Durban is going to be sort of a very nice sort of curve where in some cases, let's just say we are in Durban here, 600 kilometers away, okay? And this is where we stopped, say, in Mooi River, which was 400 kilometers away, and we stopped in Mooi River for some relaxation time. Okay, we arrive in Durban, but we were just waiting for, let's say we arrive at a hotel, and we were waiting for the time to get to the hotel room, and that's the time. So we started at home at, say, 6 o'clock in the morning, and we got to the hotel room at, say, 5 o'clock in the afternoon. And this was my journey 6 hours after. Then we were here, this is hour number 7, so let's say 6 hours. So let's say this is 11 o'clock, this is 12 o'clock, and this is, say, 4 o'clock. So 1600 hours, and this is 5 o'clock, which is 1700 hours when we finally got to our hotel. So what I could do here is I could say, well, if I travel 400 kilometers in 5 hours, I could say that the average speed for this journey, and please hear how I say it, the average speed for this journey was 11, or 400 divided by 11. So the change in distance divided by the change in time. So 400 by 5, sorry. Okay, so that gives me an average speed of 400 kilometers per hour. Okay, here I was at rest, there's no speed, and then here I went in 4 hours. Okay, I traveled 200 kilometers. So I could say that in this part of a journey, my average speed was then calculated as 200 divided by 4, which is 50 kilometers an hour. Okay, which is rather slow. But do you think, again the question comes now, do you think that you kept in this part of a journey that we kept a constant speed of 80 kilometers an hour? No, it's impossible. So the journey was never straight. The journey must have been something like this. You should have gone something like that. Okay, so in some cases you were going slower because you were stuck behind a truck, or you couldn't overtake, there was a car coming behind and you couldn't overtake. In other part of a journey you were going much faster, and so on and so on. So the journey is not really straight. And this is the whole thing about calculus. In calculus we're not focusing anymore on an average. We actually want to focus on at what velocity, what was the velocity of my car at this point? What was the velocity of my car at 10 o'clock in the morning? What was the velocity of my car at 10:30 in the morning? And so on and so on. So the whole idea behind the differential calculus that we're going to start doing is that we will be able to differentiate. In other words, we will be able to find what is the exact rate of change at a particular point. And this is the whole idea behind calculus, about me finding not the average speed of my journey, but finding what was the instantaneous speed at a particular point. So if I could model my journey mathematically, which is possible, I could then find at what exact speed I was going at any point in time. And this is the whole idea behind the differential calculus. So as I was saying, and I didn't actually look at this as an example. So average can often be misleading. Okay, we don't really care what the average speed between Johannesburg and Durban was. We are more interested in the speed the car was going when it was caught in the speed trap in Ladysmith, or when it was caught behind a car going at Wardens, etc., etc. So we are not focusing anymore on our average. We want the gradient at a point. So we want the instantaneous rate of change at a particular point. Okay, now let's say, for example, I'm going to take a point X and I'm going to take another point somewhere at some increment, which is h, so the increment, and that's why we have a difference between x and x plus h. So if this function is a function f of x, is modeled as y equals f of x, so if the x coordinate here is x, the y coordinate will be f of x. If the x coordinate is x plus h, the y coordinate will be f of x plus h. Now I could find the distance or the gradient between 2 points, but if I try to find the gradient at one point, what happens? I don't have a horizontal change, and since there is no horizontal change, what's going to happen, okay, my denominator is 0 because there is no gap between x and x plus h, and in that case I then end up with something like 0 over 0. So which basically means I cannot find the instantaneous rate of change by using a conventional method. I need to find this instantaneous rate of change by using limit. And that's why we introduced limit in the last lesson. So what we're going to do now is we will have to use limit so that we can, and again, remember, if h tends to 0, when you look at this function, what are you going to end up with? You're going to end up with the 0 over 0, which is what? Is a discontinuity. So what I'm going to try and do is I'm going to try and make it into a removable discontinuity. I'm going to have to try and remove this h from here. Okay, and that is the whole idea behind finding the gradient at a point. So I want to make this value of h as small as possible, as close to 0 as I can, and see what value this function takes as I try to make that value of h 0. Remember that I want to find the gradient of this function at let's say I want to find the gradient of this function, the instantaneous gradient at 2. Okay, I need 2 points to find the gradient, and that's why I cannot use a conventional method. So what I've done here is I've just taken an increment of h units, okay, to the right of 2. It could be to the left as well. And what I want to do here is I want to make this h so small that I can actually make it to 1 point. And what I want to do is I want to analyze what happens to this gradient as this point moves closer to that point. In other words, as the h gets smaller. Okay, and that's why I have to use limit. So my average gradient here will be, or calculating the limit when h tends to 0 of, okay, the function at x plus h, in this case 2 plus h, because remember I'm going to start from here, at 2 plus h, okay, minus the function at 2 over h, in other words 2 plus h minus 2, which is h. Okay, now the function is the function f of x equals x squared. So if I was to calculate that, I would say, so this is the limit when h tends to 0 of, and this is 4 plus 2 plus 4h plus h squared. Remember that that is f of x is the square of x. So if my x is 2 plus h, the square of 2 plus h is this. Okay, minus 4 over h. And again, this is one of those limits that if I was to substitute the h by 0 here, I will end up with a 0 over 0, which again, as we said before, is meaningless. So therefore, I need to do something. What is that something? Well, let's see what happens here. I can simplify the 4 minus 4 because 4 minus 4 is 0. And with the expression that I've got in the numerator, I could take out a, remember, I haven't calculated a limit, so I need to keep it. I could take out an h common factor. And in the numerator, I'm going to have 4 plus h over h, and here is what I was looking for. Now I can safely simplify those two, and the moment I've simplified that, I've basically removed the discontinuity. Once I've done that, I can now safely substitute h by 0 and obtain a value that has meaning, in this case the value of 4. So I could say that this function at the point where x is equals to 2 has a gradient of 4. The next part of the question now is what I'm going to do is, does the function has the same gradient as x is equals to 3? Would it be the same? Is there a pattern? And that's what we're going to take care in the next session.